Last week we introduced the idea of energy of reactions, looking at does this reaction give off or absorb energy, and you got the chance in a lab to calculate delta H, which was really fun. This week we are going to be looking at another aspect of does the chemical reaction happen, and that is with the degree of chaos or the degree of entropy that a chemical reaction either produces or goes against. So the concept today is chaos, and the fact that the universe loves chaos and is running towards chaos, and chemical reactions are a part of that. You're going to get this concept here today in chemistry, and then again in physics. Matter of fact, physics is doing this same concept, or they just finished the same concept last week. So you'll see it again. This is not the only time that you will get to experience chaos in science class. So entropy and free energy. When we look at the question, will a reaction occur, there is more to it than just gaining or losing thermal energy. That's a big piece of it, because if a reaction gives off energy, it is much more likely to happen on its own than if an energy absorbs than if a reaction absorbs thermal energy. Reactions that give off thermal energy are much more likely than reactions that absorb thermal energy, but that's not the only thing that comes to play. There's also the question of the orderliness of the products and the orderliness of the reactants. So how much chaos is created? Reactions that are endothermic, meaning they absorb thermal energy, can spontaneously occur even though they absorb heat if they create chaos. Because chemical reactions that create chaos happen spontaneously. Anybody think of a chemical reaction just off the top of your head? What's a chemical reaction that makes chaos?
Fire.
Yeah, fire is a great one. Yep. A piece of wood is a lot more orderly than all the little bits of smoke particles in the air and all the thermal energy that's been given off. Right? Explosions definitely create chaos. Something is orderly, and then it's all over the place. Chaos, right? So reactions that are endothermic, that absorb heat, can still spontaneously occur if the amount of order or disorder is, if the amount of chaos created, the amount of disorder created is big enough that it overcomes the need to absorb heat. So the amount of order or disorder in the products and the reactants must also be considered. And there's math for this. Yay. We love math. You will do much more of the math of enthalpy and entropy, not enthalpy, the math of entropy physics class than you're going to do in chemistry class. But you will see some of the math today. Okay, so if we're going to be able, after the end of the next section, in chapter 14, we're going to be able to analyze a chemical reaction and do several kinds of mathematical analysis to the energy there and say, does it gain or lose heat? Does it create or go against chaos? And some other measures that we're going to be able to do in a little bit. And then we'll say this chemical reaction will definitely happen. If you expose this chemical to this chemical, they'll get right to it and it'll be a chemical reaction. Or you can mix these two things all day long. And even though, in theory, this reaction might be able to happen, it's not going to because of various factors. So we're asking the question and learning to answer the question, will this chemical reaction happen? Part of the answer is, does it absorb or give off heat? Part of it is, does it create or go against the trend towards chaos that's out there? Okay, so here's just an example. Spontaneous endothermic reactions. Try this at your own risk. Yeah. Okay, so this is, they're taking the temperature, they don't hold it there long enough for you to have read it, but it's at room temperature, 20-ish degrees. And here we have baking soda and citric acid. And when you combine baking soda and citric acid, They need a little water to be in the reaction medium. It foamed, and then it's very close to 0 degrees. So it got really cold, and you can see the temperature dropping. So this is an endothermic reaction. The reaction absorbs heat, but it happened on its own. You didn't have to do something bizarre to make that happen, okay? And so this is an example of a spontaneous endothermic reaction. And the reason that it happened on its own is because there's greater chaos in the products than there is in the reactants. For some reason, it never wants to leave YouTube. So just go to okay? So reactions that absorb heat are endothermic. Reactions that give off heat are exothermic. And the majority of the time, spontaneous reactions are exothermic. They give off heat. But some that absorb heat, like that one I just showed you, can still happen if the chaos is in favor of it. Okay? There's a lot of words here. I'm actually pausing to give you a moment just to write this down. So I can get my mouse to it. So the measure of randomness or the measure of chaos in a reaction is called its entropy. It sounds like enthalpy. Enthalpy is heat. Entropy is chaos. So neither of these words are very helpful for you to remember what they are. Entropy is chaos. We use S to represent it. That's also not helpful. Because entropy, maybe it's E, you know. Oh, it's chaos. Maybe it's C. You know. Entropy and S, not very helpful terms, but that's what they are. So when you see S in a chemical reaction or an equation, we're talking about how much chaos is present. The logic for this math is exactly the same as the logic for calculating heat. I look at the heat of the products minus the heat of the reactants, and I get delta H. I look at the chaos of the products minus the chaos or randomness of the reactants, and I get delta S. This is the change in chaos, change in the degree of randomness in the reaction. With delta H, I wanted a negative term. A negative term meant that the heat was flowing out of the reaction and it was favorable. For delta S, I want a positive term. So this is a point of confusion for lots of people. Is they're going to subtract the summation of delta H minus the summation of delta H. And if you get a negative answer, you say, okay, that's good. The reaction is going to give off heat. It's going to spontaneously occur. It's exothermic. And then you start doing your S calculations, and you have the summation of the S of the products minus the summation of the S of the reactants, and you get delta S, and this time though you want a positive number. Because you want the products to have a larger number. You want the products to be, you want the products to have a smaller number. No, you don't. I'm getting confused. Yeah, you want this to be positive, and so you want the products to be bigger, right? More chaos, more randomness at the end of the reaction gives you a positive delta S term, which means the reaction is likely to happen. You're going from a smaller amount of chaos to a larger amount of chaos, smaller amount of randomness to a larger amount of randomness. So a positive delta S means the products are more random, and the reaction is more likely. Okay, so if you have a negative delta H, that's good. If you have a positive delta H, I'm not sure that reaction is going to happen. It's absorbing heat. If you have a positive delta S, though, that's good. The reaction is probably going to happen. You're increasing chaos. If you have a negative delta S, not sure the reaction is going to happen. It's going to a more orderly state. Okay? So we have to consider both things when we ask the question, will this reaction occur? Increasing or decreasing enthalpy influences how likely a reaction is, as does increasing or decreasing entropy. So there is another letter we get to use. We get to use G now. So we've used H, we've used S, and now we get to use G. And at least G makes sense because this is named after a chemist who started doing all of this thermochemistry math and explaining it. His last name was Gibbs, and so we call it the Gibbs free energy equation. At least it's Gibbs free energy, we use G. Enthalpy is H and entropy is S. Not helpful. Gibbs free energy is G. Okay, we're good about that. And we express this as the change in Gibbs free energy, delta G. And what I do here is I take my delta H term from the delta H reaction equation, and I subtract a term that is the temperature in kelvins where the reaction is happening times my delta S term, and I get delta G. So this takes into account the change in heat and the change in randomness and the temperature at which the reaction happens. And I can use those things and come up with one answer that will tell me, will this chemical reaction occur spontaneously? Okay. So Gibbs free energy is the one answer to the question, will this chemical reaction happen? So if a chemical reaction has a very large negative delta H, then delta S may or may not matter. But if it's got a positive delta H, and I'm not sure this is going to happen, then the delta S can tell me if it's going to work. Okay, so I take into account both the change in energy and the change in randomness, and I can figure out if the chemical reaction is going to happen. Okay. Okay. I think I get to do some examples with you here in a moment. This is one of your latter slides of work. As we've been saying, if you ask the question, will this chemical reaction happen, there are two influences. There's the influence of change in heat and the influence of the change in orderliness or randomness. So the more negative your answer for delta G, the more likely that the reaction will occur spontaneously. So if we have a very largely negative delta G, then the reaction is going to happen. It's going to happen on its own, and it's probably going to happen very fast. If we have a positive answer for delta G, it will probably not happen on its own. If we have a just very slightly negative answer for delta G, then it will probably happen on its own, but slowly. Okay, so delta G is the key term that we want to be able to dial into. Because there are two things that we're measuring, and there are two possible answers for each of those things. It can give off or absorb heat, and it can create or go against randomness. Then there are four possible kinds of reactions, right? There's the endothermic reaction where it absorbs heat, like the mixing together of the baking soda and the citric acid, or like the mixing together of ammonia and Epsom salt would be another one, where it absorbs thermal energy. So it's endothermic. And if it were to decrease entropy, like if you were to mix together two liquids and they absorbed heat and formed a crystal, so it went from from more random to more orderly, then that would be going the wrong direction with regard to chaos and the wrong direction with regard to heat. And if you have a positive number and you subtract a negative number, then you're adding a positive number plus a positive is going to give you a positive answer. And these kind of chemical reactions are very unlikely to occur. If you mix two liquids together and they're going to crystallize, they're going to form a precipitate, a solid precipitate, that increases the orderliness of the universe in your beaker, right? And if that were to get colder too, that reaction will almost never happen on its own. You would have to do that reaction in some kind of crazy situation that gave it a whole bunch of energy to get it started, okay? So that's very unlikely to occur if you had a big positive G. But you can see that there are other ways to have those terms come out. And this is your last slide of text. You could have a reaction that is endothermic. It absorbs heat energy, but it increases chaos. It increases entropy. So you mix two things together and it gets colder, but it also goes from solids to a liquid or solids to a gas. And so you're increasing the randomness and the chaos of the universe in your beaker. And so this is a positive delta H term and a positive delta S term. Depending on which one of these is bigger, when you do a subtraction, you may get a negative answer for delta G or you may get a positive answer for delta G. This could be a spontaneous reaction. If you notice in the little video that I showed you where they took a powder, a solid baking soda, and a powder or a solid citric acid, they mix those two powders together. We have solids now. And then you add water to it. That's a liquid. When the reaction happened, it bubbled and foamed. So it released a gas. Now a gas is much more chaotic than a solid. And so we increased the randomness of the universe. Entropy went in a positive direction. So even though it got cold, and this term says the reaction may not happen, this term was very large, so when you have a smaller number minus a larger number, you wind up with a negative answer for delta G, and that reaction was spontaneous. It did happen, okay? But even if it's the other way around, if your delta H term is bigger and you're subtracting a positive delta S, then numbers, I'm just going to pick numbers like 10 minus 3, you're going to wind up with a positive answer for delta G. And you're going to have a reaction that probably would not happen. So the more positive delta G is, the less likely the reaction is spontaneous. The more negative delta G is, the more likely it's to be spontaneous. Okay. You could have a situation where it's exothermic, where the reaction gives off heat, so it warms up as the reaction happens, but it has decreasing entropy. So your delta H term is negative. Yay, good for you. That's what you want. But then we're subtracting a negative. So subtracting a negative is an addition statement. So depending again on how large the magnitude of these two numbers is, we may get a positive or a negative delta G. So here we have a reaction where it gives off heat, but it's becoming more orderly. And so depending on which term is bigger, we may have a spontaneous reaction or we may not. If your delta H term were, and again, I'm just going to randomly pick numbers. If your delta H term were negative 10, and my delta S term were negative 3, negative 10 minus negative 3, negative 10 plus 3 would be negative 7. That reaction would happen. Spontaneous reaction because delta G winds up being negative. But if it's the other way around, if my delta H is negative, my delta S is negative 10, sorry, negative 3, negative 10. Negative 3 minus negative 10 would be negative 3 plus 10. I'd have a positive 7 for my delta G. Reaction probably would not occur. So it depends on the magnitude of these numbers in these two situations, okay, as to whether or not the reaction is going to happen. The last situation is a reaction that is exothermic. It gives off heat, and it increases entropy. This is something like lighting a piece of paper on fire with a match. Well, it's going to give off heat. As that piece of paper burns, it's going to give off heat. It's exothermic. And we're going from a solid sheet of paper, pretty orderly, to smoke and light and pieces of ash flying around, lots more chaos. So I've increased chaos and I've released heat. That chemical reaction is always going to be spontaneous because any negative number minus any positive number gives me a more negative answer than this was to begin with. And so I'm going to have a spontaneous and probably a very fast-moving chemical reaction. Okay? So delta G, Gibbs free energy, is the key to answering the question, will this reaction happen? Let's look at some examples. So, is the following reaction spontaneous at 0 degrees Celsius or 273 K? So, I'm going to do this in my freezer. I'm going to take silver oxide and 2 moles of hydrochloric acid, and I'm going to combine them together. Will anything happen is what I need to answer. So, the first thing we're going to do is calculate delta H. This was last week's math. Okay, so let's calculate delta H, the enthalpy and the entropy. So here's my big, nice, huge tables that we get to use from your textbook. And here's my silver oxide, silver chloride. My delta H value is negative 127, my delta H formation. And my delta S value, my entropy value, is 96 joules. Okay? Then I need to find my other things involved. The hydrochloric acid has a negative 92.31 and a 186.9. Water as a liquid, negative 285.8 and 69.95. And silver oxide, here's my numbers for that. So you don't have to calculate these numbers, you just have to look them up. Okay, look them up on a table, write down the numbers that you need, move on about your life. So I'm going to go back now. Here's all the numbers I just got off of my table. So I have to calculate delta H. Delta H of the products minus the summation of the delta H of formation for the reactants. Products minus reactants, so let's plug in the numbers. I need all of the delta H of formation numbers from this first column. Oh, come on, mouse. There you go. So, negative 241.8, that was here, time plus 2 of negative 127.0. Here's my negative 127.0, and 2 of them, because in my reaction I have 2 moles of hydrochloric acid. So I have to keep the coefficients the same. Minus 31.1 plus 2 moles of negative 92.31. These are just all the numbers I got here. For these substances, I have to keep all the coefficients the same in this addition sentence. Okay? Just a little bit of very simple algebra. Multiply first, order of operations, then add, and then subtract. Okay, so the summation of the heated formation for my products minus the summation of the heated formation of my reactants. So negative 495.8 plus, because I'm subtracting a negative number, gives me this answer. So my delta H is a negative number. That's good. This reaction gives off heat. So yay. This reaction may happen. The delta H tells me that it may happen. Okay? So let me just put that number up here so I have it in the future. Write that down. That's my delta H. Okay? Move along. Now I need delta S. So now I need all of these numbers, right? Same exact thing. My delta S value for silver oxide plus twice my delta S value for hydrochloric acid, because there's 2 moles. Okay, that's the reactants. I'm sorry, that's the products. Minus the reactants. 121 plus twice this. So keep all the coefficients the same, just use your values. Products minus reactants. Very little bit of simple algebra here. Multiply first, then add, and then subtract. So 381.4 minus 495.1. I am going, reactants to products, I'm going from a higher to a lower amount of entropy. So my delta S value here is going to be negative. So now I'm not sure what's going to happen in this chemical reaction. It's giving off heat. So that means that it may happen, it may be spontaneous, but it's increasing order. It's going against chaos. So I'm not sure. I'm not sure if this chemical reaction is going to happen. I've got to use the Gibbs free energy equation. So I'm gonna put my delta S value up here. Okay, so my delta H was negative, and so is my delta S. The units are not the same, so we need to convert delta S to similar units. Notice that delta S is in joules per mole, and delta H is in kilojoules per mole. We can't do this. It's not apples and apples, right? So I've got to fix my units here. So if it's 113.7 joules, how many kilojoules is that? This is 1,000 joules. I need to fix my decimal point real quick. So my new delta S is 0.1137 kilojoules per mole units Kelvin. Okay, now, Gibbs free energy. Delta H minus T delta S. Delta H, this number I got up here, minus temperature. What was the temperature when I mixed these two things together? The question said I'm going to do it at 0 Celsius or 273 Kelvin. It's got to be in degrees Kelvin here. Times my value for delta S. So delta H minus T delta S. Delta H minus T delta S. And then again, the math is very simple. It's nothing harder than a little bit of multiplication, a little bit of addition and subtraction. The math is not hard. It's keeping straight what you're doing here. So absolutely nothing changed between those two lines. Awesome. Copy paste. Multiply here, and I get this. Now I'm negative 280.08 minus a negative number, so that's actually an addition statement. Add them together. And my answer for delta G is negative 249.0399. Is that a small negative number or a relatively large negative number? A relatively large negative number, right? So then that reaction is spontaneous and will occur, and will probably occur fairly quickly.